Okay, calculus, we didn't actually finish this problem. Remember, to find the n of t, technically we're supposed to take t prime of t and divide it by the magnitude of t prime of t, which really is just looking at the ratio of those two, the x and y components. Now you notice by 48:36, that's a 4:3 ratio, so this will end up being 4:3:5. So anyway, the n of 1 should be -4/5 I plus 3/5 j, just by the ratio. Because this thing ended up being 1/25 or 12/25 times that. So I digress there. So the problem happens here in three-dimensional spaces is that there's an infinite number of these. In two-dimensional spaces, there's only two. There's two things perpendicular to the tangent line, one going towards the shape and one going away. The principal unit normal vector is the one that goes towards the concave side. So if it's curving downwards, it's the one going down. If it's curving upward, it's the one going up. It's really the one going across the shape from the tangent line, essentially. In three dimensions, though, this is much harder to visualize. It's still the same truth, technically, but if you have like a 3D shape curving around here, it's hard to tell what's going towards the shape, what's going away from the shape, when there's infinitely many things doing it. In general, part of acceleration acts in the line of motion, and part of it acts perpendicular to the line of motion. In order to determine these two components, you can use the unit vectors t of t and n of t, which serve in much the same way as I and j do, representing vectors in the plane. And it has to do with curving, right? If a three-dimensional shape is curving, part of your acceleration is going in the direction you are currently going, and part of it is helping it turn. So the acceleration vector, if r of t is the position vector for a smooth curve and n of t exists, there exists an acceleration vector a of t that lies in the plane determined by our tangent vector and our normal vector. The coefficients of t and n are called the tangential and normal components of acceleration and are denoted by a sub t and a sub n. How is each one calculated? It's these formulas below. A of t, so the tangential component is the derivative of the magnitude of v, which is the acceleration component dot t, which is also equal to the velocity function dot the acceleration function divided by the length of the velocity function. Now for a sub n, it's the magnitude of v times the magnitude of t prime, which is the dot product of a and n, which is the cross product, the magnitude of the cross product of v and a divided by the magnitude of v, or the square root of the magnitude of a squared minus a sub t squared. And this is primarily due to the a squared plus b squared equals c squared. So if you can get this one and you have the magnitude of a squared, the magnitude of a, it's just like Pythagorean's theorem. There's two components working towards one total final outcome. And that's a lot. On the next page, we're just going to do number 4. Dealing with this in 2D is enough, I think. Find the tangential and normal components of acceleration for the position vector. Actually, it's 3 dimensionals, but it's fine. It's easy to work with. 3ti minus tj plus t squared k. So our velocity function is 3i minus j plus 2tk. Our acceleration function, these two are gone, it's just 2k. Now it says the tangential component of acceleration is the dot product of the velocity and the acceleration. So that's 3, -1, 2t dot 0, 0, 2, which should just be 4t. So the rest zeroes out. Now it says the magnitude, we need the magnitude of the velocity as well in the function, because this thing gets divided by the magnitude of the velocity function. That's the square root of 3 squared plus 1 squared plus 2t squared, which is the square root of 10 plus 4t squared. So in total, a sub t equals 4t over the square root of 10 plus 4t squared. Now, it says a sub n can be calculated in a few different ways. We can either take the magnitude of a squared minus a sub t squared, or we can do it with a cross product divided by that same magnitude of v. We're going to go ahead and do the cross product just to see what it looks like in this case. So we have 3, -1, 2t, 0, 0, 2. So it's I times -2 plus j times, well, minus j times 6 plus k times 0. So namely, this is -2i minus 6j, and we need the magnitude of this over the square root of 10 plus 4t squared. The magnitude is the square root of those two numbers, coefficients squared, so that's the square root of 40 over the square root of 10 plus 4t squared. So this is an, and this is at. Now what do we know about an and at? They're just the components. So we have at is 4t over square root of 10 plus 4t squared. An equals the square root of 40, the square root of 10 plus 4t squared. And we'll finish this off in the last two problems in the last video.